Afternoon or evening, depending on where you are in the world. My name is Doug Evans, and I'm the director of the International Institute for Environmental Studies. And I want to welcome you all to this lecture series in environmental and human health risk assessment. I'm very pleased that you're joining us. Just a couple of housekeeping details before we start. I would ask that if you're not speaking, if you would keep your microphone muted, that just prevents background noise and won't interrupt the talk. Also point out that you can send questions to the speaker using the chat function on your Zoom screen. I also want to start by introducing Dr. Hui Dang. Hui is a lecturer and researcher at Trent University. He works in my research group. And first of all, I want to thank him because he's been responsible for organizing and putting together the excellent selection of lecturers that we have for this series.
Thank you.
And he's also, and he's also responsible for making sure that things work along the way. So if you have technical issues or something, you could email him or you can let him know, and he will be able, hopefully, to solve the problem. I also should indicate that most of our lectures will be put onto our website, recorded and put on our website. So if you happen to miss one along the way, you can always go back and have a look at that lecture at your convenience. And now I'd like to introduce our speaker for the first lecture. It's a great pleasure for me to introduce Professor Beate Escher. Dr. Escher is a professor at Eberhard Karls University in Tübingen. And if I can make my slides move here. Okay, not sure why I can't make my slides move. Oh, there we go. Okay, as you can see on your screen, Professor Escher is a professor in environmental toxicology at the University of Tübingen, also lecturer at the ETH in Zurich and head of Department of Cell Toxicology at Helmholtz Center for Environmental Research. Did her BScs at University of Constance and Rutgers University, master's at Constance, and did her PhD at ETH Zurich. She's a member of the German Council of Science and Humanities and an associate editor with the Journal of Environmental Science and Technology. And as you can see, she has an outstanding publication record. In terms of the research interests, Professor Escher works on modes of action based environmental risk assessment for a number of different types of organic compounds. Also on the effect assessment of transformation products and disinfection products. And her work is trying to close the gap between exposure and effect assessment using approaches to linking bioavailability as well as modeling of toxicokinetics and toxicodynamics. She also does work in areas of passive sampling and effect-based methods for water quality assessment, dosing methods for compounds that are rather difficult to work with, like very hydrophobic and volatile compounds, and has developed new in vitro assays for bioaccumulation and toxicity assessment. We're extremely fortunate to have her give this introductory lecture, and so I want to thank you, Dr. Escher, for doing this for us. I also have to apologize. I'm here in Switzerland at the moment, and I'm at a conference, and so I'm not going to be able to stay for the entire lecture. So I'll catch it up once it's on the website afterwards. But I'm sure it will be a stimulating lecture, and so I thank you once again for doing this for us, and I'll turn it over to you.
Thank you very much. So now I have to figure out how to share the correct screen. So can you see my screen now? And in a minute, you should also be able to see my slides.
Yeah, everything's very nice.
So the slideshow should be coming. Yeah, now. Is that good now?
Yeah, we got it. Thank you.
All right, so thanks very much for the kind introduction. Thanks for having me. I don't know why I said so quickly, oh, no problem, I can do this. Then I realized it's a really short time to do an introduction to environmental risk assessment. So I think I can't really go very deep in detail, but I hope at least with today's introduction, I'll get you framed so you can capture a few of the terminology and have a general concept of how environmental risk assessment works. And I put a bit of a focus on the European legislation, acknowledging that, of course, you come from all areas of the world, but I thought it might still be interesting. And it's also very general. I think there's a lot of commonalities, at least from the regions of the world that I'm aware of. So we don't have a lot of time, so I go in medias res. Please interrupt me and ask questions or write a little note whenever something is not clear. So first question, of course, what's risk in the context of environmental risk assessment? We have to answer the question, does a chemical reach the environment? Does it reach us, human beings, and in which quantities? And then we have to answer the effect or hazard question, so how toxic is a chemical? And a combination thereof, the probability of exposure occurring is then the risk. And we have a few terms that I just put down for your convenience. We basically abbreviate ERA for environmental or ecological risk assessment, HHRA for human health risk assessment, and we try to make that differentiation between, and that's a bit fuzzy also in the literature, but in theory, hazard is really the substance or the event that has the potential to cause harm, and the risk is then the probability that that harm may occur. So if you have something super toxic, if you take the necessary precaution, you can still work with it in the lab. You're probably aware of that from your own lab work. But even if something doesn't cause a lot of harm, but you immerse yourself in it, then you still might have an appreciable risk. So we have to really keep these two terminologies apart. I'm focusing here on organic chemicals. But we have to differentiate between different types of chemicals, and actually legislations are also differentiating. So I'm focusing on the way industrial chemicals and industrial products are assessed. So by following the REACH regulation. This also includes consumer products. Biocides typically have specific regulations. And then also it's really hard to regulate geogenic and natural chemicals. At least they don't fall under these type of legislations we're talking about today. We also have to keep in mind that there's also transformation products, and they're not purposely put into the environment, but they're just happening to happen during natural attenuation processes or during disinfection processes and the likes. And we have to keep in mind that that those may also pose a risk, even though they are not explicitly included in the regulations I'll be talking about. We do have a problem, a huge gap between the known chemicals. In the meanwhile, there's 140 million chemicals known and registered in the CAS registry. We assume that there's about 100,000 chemicals in daily use. And this figure is now from UNEP report, and it basically states, well, out of those 95,000 industrial chemicals, we know very little. We have only for a couple of hundred biodegradation half-lives, and that's basically relating to persistence. So very important, a chemical that's not degrading will stay potentially for a very, very long time. And so that's a big hazard indicator. Then we have about 1,000 chemicals, so less than 1%, bioconcentration factors, how much they accumulate in biota. And we have only for a few more acute aquatic toxicity data, let alone chronic toxicity data, which we really need to be protective of the environment. So it's a huge task. And that task has basically been something we have realized probably the latest in 1962 with the book Silent Spring that put attention on the deleterious effects of DDT. And that really started a lot of action or management of chemicals, more or less. We have in Europe, we have legislations coming in already as early as 1967. In the 70s, different legislations were implemented, more specific ones, not just classification and labeling. In the 80s, the field moved towards hazard ranking, and in the 90s, many countries and regions implemented risk assessment legislation the way we know it now. At the same time, agencies were formed like US EPA, Environment Canada, now Environment Climate Change Canada, the German UBA, which is equivalent to EPA, and the likes. In Europe, there was a big milestone in 1981 when they started to basically differentiate between chemicals that were already there, and we had to do a retrospective risk assessment, looking back what had happened. And there were about 100 substances that were then collated in a so-called European inventory of existing chemical substances. And then anything that came new was in the European list of notified new chemical substances. And that they were about 5,000 chemicals in that list, and the other one about 100,000. And so from that time, more formal legislation started in 1996. A guidance document, the technical guidance document of the European Union was issued. It was revised to 2003. It was really a paradigm shift, a major shift into formalizing risk assessment. But that wasn't the end of it. In 2001, the European Union published a white paper, and that was very visionary. It turned to the precautionary principle, which is also one of the founding principles in the Maastricht Convention of the European Union, so very important. And that was really the basis for the present chemical law REACH, which entered into force in 2007. At the same time, there were international treaties like the Convention of, I only named two, the Convention of Long-Range Transboundary Air Pollution, or 2004, the Stockholm Convention on phasing out the persistent organic pollutants, POPs. In Europe, we have this regulation REACH, which stands for Registration, Evaluation, Authorization, and Restriction of Chemicals. And these are actually the steps. Over the last 10 years, since it entered into force, chemicals starting at high tonnages from 1,000 all the way down, so the deadline for 1 ton per year chemicals was just a couple of months ago, that these chemicals and substances needed to be registered. And it's not only concerning Europeans themselves, but even producers, and not only producers, but also importers needed to submit a registration dossier. So even a chemical that's been produced anywhere in the world, if it's imported into Europe, it falls under the chemicals regulation REACH. And the next step is then the evaluation. The registration dossier, which is submitted by the industries or by consortia, is then evaluated, and initially for completeness and validity, eventually for the substance itself. And if a chemical turns out to be persistent, bioaccumulative toxic, or has other concerns, then it can be defined, and that's a long process, and I love to talk about that, but that would lead us into the evening. That it can be defined as a substance of very high concern, and that includes carcinogens and these persistent bioaccumulative and toxic substances, and they undergo an authorization process, eventually potentially leading also to restriction of use or entire total ban. Similar regulation of chemicals in the US for industrial chemicals is the Toxic Substance Control Act. Probably some of you can talk about that much better because I'm not that familiar with. And both the European and the US regulation turned out to be really slow, and not many risk assessment accomplished. So the Europeans invented REACH, and the equivalent speeding up of the process and modernizing the process was the Frank R. Lautenberg Chemical Safety Act for the Chemical Safety for the 21st Century Act, which amended TSCA by additional mandatory requirements for EPA to evaluate existing chemicals with clear deadlines, new risk-based safety standards, and higher transparency. So there's really a lot of similarity with what's been happening in Europe. There's many other legislations. Korea has K-REACH, very similar. Australia has a very similar legislation. So I could go on and on and on, but I just want to keep it brief for today and just give you the frame for where we are looking into. But now we can go to the objectives of risk assessment. It always has these elements. They are sometimes termed a little bit differently. They actually in REACH, they're termed a little bit differently than it's written down here, but I think that's the most logic way we can build up risk assessment. And so this is for environmental, but it's very parallel for human health. And you start with a hazard assessment. You want to find out, is this chemical a potential threat? You know, is it, does it do any harm? Is it toxic? Does it cause any specific effects? Is it bioaccumulative? All sorts of things. Then we do in parallel exposure assessment with an effect assessment. And exposure works like you look at the emissions, you measure environmental exposure. If it's a new chemical, you set up fate and transformation models to come up with a so-called predicted environmental concentration. If you have measured values, that would be equivalently called measured environmental concentration, so MEC values. On the effect side, we work with laboratory tests, but they are for single animals, for short-term testing, like a fish test for 96 hours. But we want to be protective for the entire ecosystem for the entire future, for a long future. And so we have to extrapolate, put some safety factors to derive a predicted no effect concentration. And then it's really simple. We just put the ratio between the predicted environmental concentration and the predicted no effect concentration. That's our risk quotient or hazard quotient, or different legislators call it differently, but in a way it's a measure of the risk. And that's the part of risk characterization, which is followed by risk management, because you also have to then decide what you do about. But that goes beyond of what I'm going to be discussing with you today. So first step, you still following me? Am I too slow? Too fast? I'm never too slow.
It's perfect.
It's good? It's good? Okay. All right, so first step is hazard identification. So that's this, what I mentioned already, the inherent potency of a chemical to cause harm. And we evaluate data on harm to the environment, like lethal effects for representative test organisms, we go into that in a minute, or health hazards for human beings, diseases, etc. And that hazard identification ends with a label on the box with the chemical or the package. And we have a globally harmonized system, which is also used in the European Union, but in many other countries, that give a defined hazard symbol. So when you have a truck driving from one legislation area to another one, from one country to another one, from one language to the other one, that you can unambiguously define what's the hazard with that chemical. And you can all go into your kitchen cabinet and turn the bottles around, and you might find any one of those signs, hopefully not an exploding bomb, but it's very likely that some of the more severe cleaning agents or so have this sign of damage may cause damage to the aquatic environment, this dead fish, dead tree symbol. Another symbol that you might find is health hazard, so that are chemicals that are cause or are suspected to cause serious health effect. If the effect is not as severe, you get at least an exclamation mark, which means that either the effects are less serious or we're less certain about the effects. And all of that you can read up in the global harmonized system of classification of labeling, which is a UN document. The next step, and still part of hazard assessment, is PBT assessment. So we have to ask ourselves how fast or slow a chemical is degraded, to what extent is it accumulated in organism, and how toxic it is. And not only how much you need to kill an animal or to induce an adverse effect, but also which mode of action is the chemical exhibiting. So is it causing cancer? Is it causing skin irritation? All sorts of these things. And there's a few chemicals, and I'm going a little bit away from legislation, but I just want to point out these chemicals, which are clearly PBT chemicals. They were made for a purpose, but unfortunately they're still there to last. And those are the initially dirty dozens, the persistent organic pollutants that are starting with DDT, but also PCBs and others that have accumulated over the years in the environment, in all of us. So every single one of us, I'm afraid, is carrying some of these PCBs and DDTs in their blood and their lipid tissue. And that was early agreed, and that they should be phased out, at least as best as possible. There's a few exceptions, like DDT as malaria disease vector. It's still allowed to be in use, but these compounds are being phased out worldwide, because we all know chemicals will not stop at the border, and they will distribute according to physical-chemical principles, not according to country borders. And the Stockholm Convention chemicals are continuously appended, so there were additional chemicals included every 2 years, basically. There's a clearly defined process, and many of our modern chemicals, like the perfluorinated compounds, are added to this list. And what these chemicals have in common, that they're acknowledged as really substances of very high concern. So we don't have to find that out anymore. But for the new chemicals, we have to find out what these criteria are, what these substances are, and there's clear criteria. For persistence is that these chemicals are not well degradable in the environment. Degradation half-life in aqueous environments of more than 2 months or so, but that they're highly bioaccumulative, expressed as high KOW or high bioconcentration factor, BCF, or bioaccumulation factor, BAF. That they have a potential for long-range environmental transport. That's in addition to the national legislations, that fact that not the people who use the chemicals and profit potentially from the chemicals, but the ones that are possibly very remote, like in Antarctica, will be affected by these chemicals. And then finally, that chemicals have adverse effect. In REACH, the idea to first do a PBT assessment was almost like a paradigm shift, because you would not assess chemicals solely based on their tonnages or the likes, but you will assess every chemical for their PBT properties and then move PBT chemicals forward to a full risk assessment, so-called chemical safety assessment. And I always have a little bit reference here on the site that you can all download from the internet if you're interested to read up. I can only touch these topics very cursory. There are different PBT criteria. We already talked about the Stockholm Convention. These are the criteria. There's other conventions, and here are the European Union PBT criteria: half-lives in water more than 40 days, bioconcentration factor more than 2000, and a threshold for toxicity, that's no observed effect concentration for aquatic species less than 0.01%. Those chemicals that are PBT, or even there's one criterion that's VPVB, very persistent, very bioaccumulative, they move on to a stricter assessment. Now with this, we kind of have the hazard assessment. Next step is that we look into exposure. And the easiest, of course, is if we can measure concentrations in different environmental compartments and get the so-called measured environmental concentration. We're basically now here at exposure assessment. However, in many cases, and then if you have new chemicals, you can't do that yet. And in these cases, you have to model the exposure, and you get so-called predicted environmental concentration, PEC values. And the simplest model is a very simple three-phase partition model that you probably know from Introduction to Environmental Chemistry, where you have to understand the air-water partitioning, soil-water partitioning, and then you can just see how your chemical distributes. That might not be sufficient, but gives you a first idea where your chemical ends up. So if you have a high KLW chemical, it might not be in the water, but it might be bound to salts and sediment particles, but it will also be very hydrophobic and bioaccumulative. So you get quite a bit of information even from these very simple models. You can make more sophisticated models. You can go from thermodynamic equilibrium models to models where you have emission rates and loss rates. You can go to steady state partitioning, and then you can include mass fluxes. You can include persistence as a function of time. So these are several levels of complexity, and I almost can't say that in front of people from Trent University, because that's where Don McKay, who developed all of this in the 70s and 80s, came from, so I should better not go into too much detail. What's important about these box models that we have phase partitioning, physicochemical properties of the chemical, as well as system properties like transport rates with moving air, etc. And our model inputs are the chemical properties and environmental data, and our model outputs are these concentrations in all boxes or in all media that we are looking at. So one example, pentabromobiophenol ether. We have in Europe an emission estimate that there's 150 mole per hour emitted into the environment, and then we can put that into a model, and then we get predicted environmental concentration in the different compartments. So we can do that with a whole comprehensive model. That's one of those European uses models, where you get concentrations in air, in water, in sediment, in soil, and in food that is in for ingestion. Next step is, now we move to the right side, is effect assessment, where we look in the aquatic environment, as an example, at short-term exposure at high concentration. That's what we can easily measure, but we are actually interested in the chronic effects and how those relate to safe levels for the entire ecosystem. So what we need to do, we need to extrapolate from single species to the entire ecosystem, and that's really tricky. And we can't do a test in the entire ecosystem. So what we do, we mimic a simplified aquatic food chain by selecting merely 3 typically used aquatic organisms representative of 3 trophic levels, and that's typically algae, water flea, or some invertebrate, and fish. And the typical toxicity test that we're using, bacteria also for wastewater treatment plants, but the typical endpoints we're using are growth inhibition assays for algae and for chronic effects, reproduction, and chlorophyll fluorescence. And this is not a typo. Both acute and chronic is 72 hours, because algae, they will divide a lot, so it's a population level, population growth measure. For water flea, you differentiate between acute lethality, which you express, or immobilization, which you express as lethal concentration for 50% of the species, for acute toxicity, and typically some sort of reproduction parameter over several weeks, like 21 days. There you derive so-called no observed effect concentration, NOAC. Similar principle for fish, 96-hour lethality is acute toxicity, and then for long-term, 40 days, 21 days, or even early life stage tests, you take the no observed effect concentration. And depending on the quality of the data, if it's acute or chronic, you select different extrapolation factors. So in principle, you can basically say, well, I'm going from my lab test to be protective to the environment, to the ecosystem. I have to have an extrapolation factor for the lab work, inter-species variability, short-term, long-term, lab to field, single species to community. So you could basically say factor of 10 each, just about it. There's lookup tables in most legislations that tell you how you do this. So you kind of do a matrix of your data that's available. If you're lucky, there's a lot of data available. Sometimes there's very little. Then you select the lowest, most sensitive toxicity data point, and you select the appropriate concentration factor, and you divide that lowest effect concentration by the extrapolation factor. And in the REACH guidance document, if you have only acute data, your assessment factor, extrapolation factor is 1,000. If you have one long-term NOAC value, it's 100. If you have two long-term results, it's 50. If you have the full set of 3 long-term results, then it's 10. And then there's also something like that we call species sensitivity distributions. And if they're from chronic data, then you can even put the extrapolation factor to 1. Then, of course, there's mesocosm field data, model ecosystems, and these are reviewed on a case-by-case study, and these are more common for pesticides. Again, an example, and that example is actually pasted directly out, copy-pasted directly out of the REACH document. So you have a chemical substance that is manufactured in between 10 and 100 tons per year. So it has a certain requirements. REACH has lots of these appendices that you forget the numbers. And so there are 3 endpoints tested: algae, daphnia, fish. The most sensitive endpoint is the lowest concentration elicited an effect. It's 0.8 milligram per liter. In this situation, we only have acute data, so we have to pick the extrapolation assessment factor of 1,000, and that leads us to a PNEC in the water of 8 microgram per liter. You can also do that for soil and sediments. Ideally, you have test organisms in these media, but if you don't have that, you can do very simple equilibrium partitioning models. So you combine the toxicity value with a partition constant, and that gives you then the PNEC in another compartment. So basically, you have to do the risk assessment every compartment. So you have PEC to PNEC in the water, in the sediment, the soil, etc., etc. All right, where are we with our pentabromo-biphenyl ether? So here we had a NOAC value of 21 days. That was the lowest of the entire list. I spare you the entire list, of 5.3 microgram per liter, because we have more than one, which you don't know, but I tell you now. We have more than one chronic value. We can set the extrapolation factor to 10, and then our PNEC is 0.5 microgram per liter. Next step is now to form the risk quotient. PEC to PNEC smaller than 1, no action. PEC to PNEC larger than 1, further investigation necessary, a refined risk assessment, or eventually risk reduction measures. And that's the case for pentabromo-biphenyl ether, so no problem in the air. It's not a volatile chemical. No problem in the water. It's very hydrophobic, so it'll stick to many other phases. But a problem, a risk quotient above 1 for the soil 7.1, and the sediment 4.5. And what actually happened is that it was phased out very early by the European Union, not only on the grounds of the risk assessment, that pentabromo-biphenyl ether, but also because concentrations in mother milks kept on increasing. And so they were uncertain about that outcome. And so for precautionary reasons, so for applying for the first time the precautionary principle, pentabromo-biphenyl ether was phased out, I think, about 10 years ago in the European Union. All right, so this was a very simple way. So we had just had acute data, we only had steady state, very simple models. But of course, you can do a refined risk assessment. You can go to chronic toxicity data, higher level model prediction, or in tier 3, even to field study and measurements. You can go one step further. We have only selected one data point, the lowest effect concentration, but you can actually use and look into the distribution of the toxicity data. So you can develop so-called species sensitivity distributions. And then you can look at the variability of the measured and modeled exposure levels, and then combining those, you can look if this distribution overlaps and if there is a potential risk therefore. So that's a bit more refined. That's also part of the accepted way of doing risk assessment. All right, so that was just a really, really fast run through environmental risk assessment. Now we go even faster through human health. But I just wanted to point out it's the same principle. We have the same boxes, hazard, exposure, effect, and risk quotient, which is filled a bit differently. So we look at the source of chemical, the exposure pathway, and then resulting in the human exposure levels. On the effect side, we have dose response assessment, extrapolation to derive no or minimum effect levels, and those are again related as a risk quotient, and risk characterization is performed. Exposure a bit more complex because we have, it's one thing is simpler. We have only one species, one human being, but we have very variable populations, elderly, young people, babies, nursing mothers, pregnant women, etc., etc. And we have exposure from very different sources. So we can define aggregate exposure as exposure to one chemical from several sources that can even be coming from different guidelines. So drinking water is differently regulated than the use of consumer products, etc. Then the total exposure is the exposure to one chemical from all the possible sources, and the cumulative exposure is then several chemicals with the same mode of action that act together via multiple routes, and then it gets really fuzzy. So all the way through to the exposome concept, which is more concept than a reality, which is the idea of totality of all exposures over the lifetime. We'll stick for single chemicals for today, but looking at different exposure routes. And as I said already, so every group, so even though we have only one species, so we don't have to deal with algae, daphne, and fish, we have only one human, but they have different lifestyles, different age, different susceptibility, so they will have also different doses. Dose is calculated really by the concentration, the medium you take in, like air you breathe, times the intake rate constant, times the uptake fraction, which is pretty high, like almost 100% for inhalation, divided by the body weight. That gives you a dose that's related to your interior, and so you can then even add up, even if one dose comes from the air, and the other one comes from food. Do you hear this background noise? Should I close my window? Do you get a lot of background noise? Because I have construction site outside.
Yeah, we do have a little bit, but it should be okay.
Okay, let me just close the window quickly. Second. I can still hear it, but I hope it's not that loud anymore.
Oh, it's perfect. Yeah, thank you. Yeah.
Okay, sorry for that. Okay, so then this is uptake via inhalation, and the same type of equation holds for oral uptake. You have the concentration of your source, like a glass of wine or an apple. You have the concentration of the source, the amount you take up from that source, and you have the uptake fraction of your chemical, and that's of course not just 100%. And that's right, you said to one for the exercises. That's when we did an exercise in another class. Now you can take the different sources, the different sources, the different food that you eat, and the water that you drink. Everything you can add up to a total oral dose. And so the Q is the intake rate, and you get those from tables, like one table from a risk assessment book. That's actually quite a good book, Risk Assessment of Chemicals, an introduction. And they tell you how much you drink and eat. Dust intake rate is maybe 2 milligrams per day, and so you can actually look up comprehensive food consumption database for all sorts of countries from the European Union. And now you can add up the different pathways. So you can, there's also dermal uptake, so I left that out, but same principle. And so you can sum up all the pathways, all the doses from the different sources and the different uptake routes, inhalation, oral, and dermal uptake. And this is an example what that leaves you with. So this is PCB, one PCB, and here your overall uptake is mainly 99.98% via consumption of fish, while when you have an alcohol to propanol, it's mainly via drinking water, and then of course the crops that feed from the drinking water, those are the root crops and that are half water themselves, and so that's their main uptake via water in this case. So it's two chemicals that have two totally different types of human exposure pathways, but leading at the end in a certain dose that is related to the internal concentration, and we can then compare this dose with a hazardous dose from adverse health effects. Any chemical is toxic. It's just the dose makes a poison, as already Paracelsus said. So what we have to find out is the safe level, the no observed adverse effect level. We again put an extrapolation factor on that to derive the derived no effect level. And basically we work with animal studies. We're not really we're not allowed to test humans, and that's right. So we have to extrapolate from the animal, experimental data with the animal, uncertainty factor from animal to human health, but also taking another uncertainty factor into account, more sensitive populations. And the derived no effect level, as we determine it term it in Europe, has an equivalent term used by other agencies. Could be in WHO, it would be acceptable daily intake. You probably heard about that. US EPA calls it oral reference dose or inhalation reference dose. ATSDR calls it minimal risk level. Health Canada calls it tolerable daily intake or tolerable intake. So all of these are pretty much equivalent in meaning. How do we get those? We get them by having some measured effect, no observed adverse effect level, and then dividing them by the assessment factors. Here we construct the assessment factors for the different processes. We have allometric scaling from mouse. It's not just a small human, but it has a different shape, and so there are something like an allometric scaling factor, which is 4 to 6, I think. There's interspecies, there's for exposure duration, there's for quality of the database, etc., and so you piecemeal the different assessment factors multiplicatively together. And then you derive different DMELs. You can derive one for long-term oral, for long-term dermal, long-term inhalation, or you integrate it and just look in relation to the internal exposure. For cancer, there's a specificity because cancer is a non-threshold toxicant, so there is no effect level, there's only a minimal effect level. And so here you start with animal data. T25 is 25% tumor incidences in a test animal, and then you convert that with a series of assessment factors, and these assessment factors are really high. So they're in the range because you really don't want to have more than 1 in a million or 1 in 100,000 risk of additional cancer cases. So you have this high to low dose extrapolation factor that's as high as 250,000. And then you piece it all together. So you have your threshold effects, you have your no observed effect level. You put your assessment factor, you get your derived no effect level, put that together with the exposure level, make sure you have the same units. If not, you go back to square one and make sure that somehow you get it to the same units. That's I would say, the mistake that's most often done when you do risk assessment, that you end up with incompatible units. And if you don't write them down, then you overlook it. And then for the non-threshold effects, you have the slope of the dose response curves. mind you, this is cancer risk, so there's no zero risk, but you just have a slope, how that goes towards minimum or a zero level. And from that, you derive, with much higher assessment factors in the 100,000s, you derive the minimal effect level. Again, you do the risk quotient exposure derived by DMEL. Next step is risk management, and I've really talked fast. I can hardly speak anymore, so I'll keep it with that, but I will still answer questions. So for risk management, that's kind of the next step. Now we have a number, which is science-based. I mean, we can discuss about every step. It's always a simplification, but it's kind of, it has a clear algorithm how you do it. And this provides the information on which you can base your risk assessment, your decisions. But for the risk management, that's also what you're willing to accept. You know, how many dead people, or sick people, not dead people, sick people you accept, how big of a biodiversity you accept in an environment. So this is also the political part, the discourse-oriented part. And both parts, risk assessment, risk and management, should talk to each other, should act together, but conceptually and administratively they are kept apart, or they should be kept apart in most of the legislations. All right, with this you had a very, very super brief introduction to environmental risk assessment, and I'm very happy to answer questions. I think it's the fastest time I ever spoke, 41 minutes. But I really wanted to give you the opportunity to ask.
Thank you very much, Professor Escher, for your this very interesting and compelling lecture to introduce risk assessment. And it's perfect time, I believe, for our attendants to have any questions. So I see that there is already 2 questions sent through the chat options. The first one is from Jaya about, does this REACH involve pesticides?
No. So REACH is exclusively, I mentioned that very briefly, is exclusively for industrial chemicals. There's a specific regulation for biocides, and biocides are non-agricultural pesticides in a way, and that is very similar to REACH, but pesticides that you put out into the field, they have a much stricter regulation. So they always need some experiments in the environment, so they have a stricter regulation. They're also in Europe under a different legislative body. They're under the European EFSA, European Food Safety Agency. Sorry, so they're regulated under EFSA. So that's a different house.
Awesome, thank you. The second question is from Jacob. So why wouldn't the PNEC be calculated using multiple species at a time?
Well, that's basically what you do when you do species sensitivity distributions. Then you really take all the data together. The idea is why you should still have more than one data point. I mean, you can't derive a PNEC from if you have just one data point. So minimum is 3. Ideally, of course, you have more. Is that you take then the most sensitive species, so the lowest effect concentration, and the paradigm behind that is that you say if you can keep the most sensitive species safe, you can keep the entire ecosystem and the ecosystem safe and healthy and functioning. That's of course a very, very simplistic way, but the way that it's done. And for the distribution, basically you also take then the lower end of the distribution, so you're not really using all of the parts, but that's just the way you have to approach it. And mind you, you should be doing that for 100,000 of chemicals. So of course, it would be ideal to know everything about one chemical, but I think at this stage it's more important to know a little bit about many chemicals, more so than knowing one chemical in perfect detail.
Awesome, thank you. So we got another question from Verena. So how representative are the test species used in effect assessment, like each EC50, of all other species of differing morphology and physiology? Is reflected in the applied safety factors or not?
So that's a tricky one. So because that's always a compromise, because you don't know, actually not necessarily laboratory test species is not necessarily the most sensitive or the most representative species. It also means it has to be a species that can easily be kept. We, for instance, keep zebrafish in our laboratories for fish embryo toxicity test. That's not a native species of nowhere in Europe. That's a tropical fish, but it spawns every morning. And our local fish would only spawn once a year, so we couldn't really do a lot of testing. And so there's always this problem of that we have to make it practical. So a lot of when I got into risk assessment, I said, oh, this is not working well, and this is stupid, and this we could do better. But you also have to recognize that you have to have kind of a convention, and it must be feasible. And that's why they kind of came to that number of species. I mean, already when you look at Daphnia magna versus Pulex, Daphnia magna has that nice size where you can actually look at it without a microscope, and that's just easier, you know. So, and that's why probably that became the most common test species that doesn't need, unfortunately, nothing about representativeness. In my long version of the presentation, I can also send you some literature. There's people who have tried to compare, but also it differs for every chemical. So there's no single rule for that.
I see. Thank you very much. So we got another question from Jacobs. So how will risk assessment evolve to encompass nanoparticles? Then likely it's going to be for...
Yeah, that's an important one. And actually, European Union has an appendix and some amendment specific to nanoparticles, but you got me cold here, so I'm not exactly sure how they're doing it. I'm sorry for that, but you can Google it within ECHA, the European Chemical Agency's webpage, excellent webpage, and I hope you'll find that document. I could look it up now, but I would probably get my computer really disturbed. But you can write me an email and I'll find it for you.
Thank you.
I know I have it in the long version of my lectures.
Awesome. So if there is any questions from the audience? Perfect. Yeah, so thank you very much again, Professor Escher, for your talk and for these nice discussions with students from different locations in the world. So really appreciate your participations. So
yeah, thank you very much for having me, and thank you unknown students. I only see a couple of you for your attendance. This was the first experience for me like that. It feels a little bit strange to talk to a computer.
Yeah.
Get the feeling you're getting really old. But I hope I could share some of the insights that this is really a topic that's really dear to my heart. And this is actually an excerpt from a class that I teach every week for 4 hours for one whole semester. So it's really a very, very short introduction. So if you want to know more, I teach it at ETH in Zurich and at University of Tübingen. So come by, say hello, identify yourself. So yeah, you're cordially welcome.
Thank you very much, Professor Escher.
Okay.
Yeah. Have a great day. Bye-bye.
Bye-bye.
Yeah, bye-bye. So to the attendance, the next week we're going to have a case from Dr. Bartram. She used to do her PhD in the University of Idaho, and she's now working as a CEO of the TIFO. So it's NGO organizations, and they work on different projects of risk assessment in different parts of the world. So she'd give us a kind of idea about how things going to be from a practical part of the thing in different study cases in Africa, in Middle East. And so it's going to be a very, very interesting talk from her, from the group, and it's the first participations from an LGO. So I really have a lot of expectations on that. So hopefully I'll see all of you guys next week on Wednesday at the same time. Thank you. Any questions you have, please send an email to me, or just let me know. If you have no questions, see you next time. Bye bye.